is what a spectrum looks like. This is the spectrum from the sun. And what we see is the output. This is called emission. There's emission of light. Here we can see the peak in intensity. So the sun emits mostly this light here, and then it goes down. But one thing to note is that this is continuous throughout here. So we call this a continuous spectrum. In fact, the sun emits all colors of the rainbow. And this is according to wavelength. And so wavelength, shorter wavelengths is higher energy, longer wavelengths is lower energy here. And so this is reverse, red, orange, yellow, green, blue, indigo, violet. So this goes violet. On the other side of violet is ultraviolet. The sun really doesn't emit much in the way of X-ray or gamma ray. And so we can see the sun's going to emit some UV here. This is sunlight at the top of the atmosphere. This is sunlight at sea level. So a lot of the UV is taken out. And then a lot of visible light, the whole rainbow of colors here. So this, again, this is continuous. And then a lot of infrared. Infrared, we feel it as heat. So when things start to vibrate, they get hot. And so this is infrared, white. Some of these dips are taken out from water in the atmosphere instead of CO2. This kind of thing. This is why it looks jagged, but otherwise it's continuous, like this black line here shows. What about a light bulb? What does a light bulb look like? Well, here's another picture of the solar spectrum. Solar spectrum, solar spectrum, solar spectrum. Pretty much the whole rainbow colors are emitted. All right, let's take a look at the lamps. If you look at light, so the colors are here. This would be violet here, red would be here. So go red, orange, and then go violet. And so if we look at an incandescent light bulb, the incandescent light bulb emits a continuous spectrum, but it has less in the blue violet region here, a little less white. It's more red in terms of color. Halogen is a little more white in terms of color, a little cooler. Fluorescent, the fluorescent, this is not continuous. Take a look, the fluorescent only emits certain colors of light. It so happens that those colors add up to white, but it's not the white light, it's not the same white light that you see from the sun, or that you see from the regular light bulb, or that you see from the halogen light bulb here. And so the fluorescent lamp, even though these colors will add up to white, just by how colors add up, it's not exactly the same spectrum. Here is a projector. Let's see. All right, so that's kind of what we expect. And so how do you make a light bulb? An incandescent light bulb. Let's see, we get the incandescent light bulb. The incandescent light bulb has a piece of metal in here. If you heat up the metal, this is tungsten. If you heat up why tungsten? Tungsten has a pretty high melting point. So if you heat up a piece of metal, do you know what happens to the piece of metal? If you heat up the metal, then you're going to start exciting electrons. When you start exciting electrons, and electrons don't stay excited forever. Eventually, those excited electrons will cool down. When they cool down, they'll start emitting that excess energy as light. Let's see. Come on. All right, there it goes. All right, so here, metal, loosely held electrons or tightly held electrons? Loose. Metals. Although, you know, this is stainless steel. Okay, I'm going to heat it. So I excite the electrons. And then, you know, I take this out. Do I want to touch it? No, it's hot. But you know what? I put my hand around it, I can feel it. You know what I'm feeling? I'm feeling infrared radiation. The piece of metal is emitting infrared radiation, and I can feel it. Heat is what it is. Well, you know what? I'm going to get a little hotter. When I get a little hotter, do you see it? It's glowing. It's glowing. We call it red hot. This is a red hot piece of metal. It's red hot because on the other side of infrared is red. So if I just heat it a little hotter, it just starts turning red. But if I continue to heat it, it'll start to glow orange, and then yellow, and then et cetera, et cetera. Pretty soon, I might get it so hot, it looks white hot. Have you ever heard of a white hot piece of metal? It's like right before it melts, it's white hot. And so it's going to start glowing white. Well, what we're doing is, you know, we're exciting the electrons, and they're going to start emitting all the colors of the rainbow. And so that's all this is. Why do they put it in glass here? They put it in glass because take a look at my metal. Do you see how black it is now? It's kind of hard to see, but the metal is no longer shiny. It's at the tip. You might be able to see it, you might not. It's black. It's black with oxide. I got a thick oxide coating there. Here is a, this is something I was supposed to do earlier. I forgot. Did somebody donate a penny to me this class? No, it was the other class. So somebody donated to me a pretty new penny here. And what's going to happen if I start heating up this penny? It's not going to look so shiny and new anymore. In fact, it's going to look you see it's starting to turn brown, and then eventually it's going to turn black with oxide. Do you see how black it is now? And so what do you think this bulb is filled with? What gas do you think? Do you fill this bulb with oxygen? No, this bulb is an anaerobic environment. There's no oxygen in here because otherwise the metal would oxidize and it'll still no longer conduct electricity. And so that's a light bulb. And so you basically can make a light bulb out of anything that has electrons, because anything that has electrons that you can excite, right? So people have come up with ideas for making light bulbs. Have you heard of a neon lamp? Neon lamp has what inside there? Neon atoms. Do neon atoms have electrons? Neon atoms have electrons. Can the electrons be excited? Yeah. Electrons can be excited. So you should be able to make a light bulb out of lots of different things. Well, one thing they tried to make a light bulb out of is hydrogen. So let's take a look. These are different things that people have tried to make light bulbs out of. First one is hydrogen. I don't know what this is. Maybe deuterium. This is nitrogen, oxygen, and mercury. Well, those all look weird. Those all look weird because they shouldn't look like that. They should look different. Should look like this. If I make a hydrogen lamp, if I make a hydrogen lamp, what does a hydrogen atom look like? And an H atom is going to look like this. An H atom is going to have a proton in the center and an electron out here. This would be the... And this electron I can excite to different energies. So for example, if I don't excite the electron much, this hydrogen lamp should start emitting infrared radiation. If I excite the hydrogen more, then it should start emitting red light. And if I continue exciting it, then it's going to emit red and orange, and then red, orange, and yellow, and red, orange, yellow, green, all the way to red, orange, yellow, green, blue, indigo, violet. If it starts emitting all the colors of the rainbow, do you know what color light that is? It's white light. And so a hydrogen lamp consisting of hydrogen atoms should start emitting white light. And so that's what was expected. But that's not what was observed. Do you know what was observed? And so this is something that you measure in a spectrometer. So let me show you what how a spectrometer works.
A spectrophotometer works. A lamp provides the source of light. The beam of light strikes the diffraction grating, which works like a prism and separates the light into its component wavelengths. The grating is rotated so that only a specific wavelength of light reaches the exit slit. Then the light interacts with the sample. From this point, the detector measures the transmittance and absorbance of the sample. Transmittance refers to the amount of light that passes completely through the sample and strikes the detector. Absorbance is a measurement of light that is absorbed by the sample. The detector senses the light being transmitted through the sample and converts this information into a digital display.
So what we have is a little bit different than that. This is measuring absorption. We're measuring emission. So we're just looking at what colors of light are coming off that bulb. That's what we're looking at. And what they observe for this is this. So they'll put the light bulb here, and if you look at the previous light bulb, we saw the whole rainbow of colors, right? And that's what they were expecting here. They make a lamp out of hydrogen, they expect the full rainbow of colors. But that's not what they observed. They didn't observe the full rainbow. In fact, they only observed 4 colors. They observed red, and this wasn't any red, because red goes over a range. You know, it goes red and then orange, a bunch of oranges. This red is red at 656 nanometers wavelength. And then a green line at 486 nanometers, a blue at 434, and a violet at 410. And only these colors were emitted. And so what that means is the electron can only be excited to certain energies. In other words, the electron can't be excited to any energy it wants. It's restricted. And that restriction is called quantization of energy. For example, we can have a continuum of energies, or we can have a quantization of energies. The continuum of energies, all the energies are allowed. We see the full rainbow. A quantization of energy, we have allowed energies, these 4, and forbidden energies. The forbidden energies are the black regions here. And so what is this likened to? Well, one of the hypotheses goes like this. One of the hypotheses is that the electron orbits around the nucleus like this. Okay, that's fine. If the electron orbits around the nucleus, if the electron moves a little faster, then the orbit becomes bigger. And the faster it moves, the further away it gets from the nucleus. The slower it moves, the closer it gets to the nucleus. So this is the basics of the orbit. And so what this is saying is that only certain speeds are allowed for the electron. So for example, the electron can move at 25 miles an hour, but it can't move at any speed until it hits the next allowed one. And so all these other speeds are forbidden, and the next allowed one might be 37 miles an hour. This electron can move at 25 miles an hour, and then it can move at 37 miles an hour, but it can't move anywhere between those. And so if you try to move the electron at 26 miles an hour, it's forbidden. It's forbidden. Well, think about like an automobile. If you tried to drive a car, you know, obviously there are posted speed limits, but the car itself has a continuum of speeds available up to its maximum speed. So you can drive any speed from 0 to whatever the max is that you want. Right? But can you imagine a car that can only drive at 25 and then 37? And then why can't you drive? Why can't you drive? And so that means all these are forbidden. And so this is allowed, but everything else is forbidden. And so this is unusual. And so this is the unusual light pattern, because this light pattern wasn't predicted by physics at the time. The physics at the time didn't work. And so what the physicists had to do is the physicists had to go back and rethink all this stuff and devise a new thinking in terms of the physics. And so, and the old physics they called classical physics. So this perplexed classical physicists, because classical physicists expect the hydrogen lamp to work like any other lamp and emit white light. And that classical physics had to be modernized, and what resulted is quantum physics, or modern physics. So we have the old classical physics and the new modern physics, quantum physics. And so, well, what's the idea behind this? Why can the electron only be excited to certain energies? And so why the electron can only be excited to certain energies? Well, one, let's actually talk, since I'm jumping right to the theory, talk about some of the vocab here. And so this is a slide from the textbook. A continuous spectrum, all energies are allowed. A line spectrum shows forbidden and allowed energies. The lines represent the allowed energies. These are discrete, and everything else is forbidden. So that's a line. So the hydrogen lamp gave a line spectrum, whereas the incandescent lamp gave continuous spectrum. It turns out not just hydrogen, but mercury, nitrogen, oxygen, all these give a unique line spectrum. And so it wasn't just hydrogen, but people tried to make lamps out of many, many different elements, including neon. Neon doesn't give white light. And this comes later, so I don't understand the organization of this. The photon and the wave particle duality come later in development. So let me talk about this later. Oops. Here's illustration of wavelength. This is long wavelength, short wavelength. That's a water wave, but when we're looking at electromagnetic radiation, it's not like a water wave. Here's white light. Here's white light giving the continuous rainbow. This would be a spectrometer. Here's the hydrogen lamp. The hydrogen lamp does not give a continuous rainbow. It gives a line spectrum. Allowed energy, allowed energy, allowed energy, allowed energy. Everything else is forbidden. Now, why would it be forbidden? I mean, somebody could forbid you from driving, let's say, 26 miles an hour in a 25 mile an hour zone, but you could still do it, right? You violate the law, but that law is different than a natural law. This one you can't violate. This is hydrogen at the top. This is mercury in the middle, and neon at the bottom. Look at neon. It's complicated. And so, can you come up with a hypothesis now? No, I can't either. So we need more observations. We can't come up with a hypothesis, we need some. Bohr came up with a hypothesis. These actually, interestingly enough, what do we want to do? You know, when you look at this here, this pattern here, do you see a mathematical pattern there? Do you see a mathematical pattern? It turns out there is a mathematical pattern there. The mathematical pattern is that the energy is going to equal some constant 1 over n squared minus 1 over n squared, where n is an integer. And we call this n final, we call this n initial. So that's a mathematical equation that fits that pattern there. Where does it come from? All right, and so eventually somebody came up with a hypothesis, and Bohr came up with a hypothesis. Bohr hypothesized that there are things called allowed orbits, and then there are things called forbidden orbits. But the question, the obvious question comes up, why are forbidden orbits forbidden? And so do you know what Bohr said? Or do you know what a postulate is? What is a postulate? A postulate, the way we're going to use a postulate is it's going to be taken without proof. We're not going to prove it. Why it is? That's what it is. It is what it is. If it is what it is, then that's all it is. And so we can't say anything more because that's the way nature is, right? There are forbidden and there are allowed, and that's all. And so all we're going to do is we're going to just try to describe the forbidden and the allowed. And that's it. And so what Bohr said, and this is coming up with the Bohr model, is he said that the first orbit is the n equals 1 orbit, and that's allowed. And then you can't have like 0.9, 0.8. The next allowed one is going to be n equals 2. And the next allowed one is going to be n equals 4, etc. And that's going to correspond to different energies. The first energy that's allowed is E1, and followed by E2, followed by E3. And so from the Bohr model, this is what we get. The electron, these are like floors of a building. And so the electron can get excited to different floors, but they can't get excited to between floors. And so one analogy is like this, here. This, we have a continuum of levels. Here we have quantized levels. The first floor, second floor, etc. And so that's it here, these stair steps. But the stair steps aren't even, you know, they start to diverge. The orbits do, the energies start to converge. And so this is what it looks like. And we can map this out using energies and whatever else. These are the energies over here in terms of joules. And then we have a radius. In terms of radius, this is angstroms. So this first orbit here is half an angstrom. The second orbit is 2 angstroms. The third orbit is about 5 angstroms. The fourth orbit is about 8 angstroms away from the nucleus. And so the electron's just orbiting here. And so we call this the ground state. The ground state is lowest energy. And so the lowest energy for the electron is n equals 1. And the only thing that can happen, the electron can't go lower in energy. That is, the electron can't crash into the nucleus. The electron's always going to stay away from the nucleus. But what can happen is the electron can absorb energy and get excited. This is what happens. But it can't absorb any energy. It has to absorb the correct amount of energy to make the jump here. And so that's where we get the quantization of energy. And so these are all forbidden. And so in terms of the Bohr model, this is what the hydrogen spectrum looks like. Well, here, talk about the jump here between energy levels. It's a quantum jump. It's not a continuous thing. It has to jump up to the next allowed one. The ground state is in the lowest energy. It doesn't have to be n equals 1, just the lowest energy state possible. And then we have excited states. Excited states is when the electron gets bumped up in energy. So this is what Bohr is thinking. You know, the hydrogen atom starts off like this. An electron gets excited, different ways to excite the electron. Pass an electric current through it. You can heat it up. You can do something. An electron gets excited here. The electron doesn't stay excited forever. It's going to drop down. When it drops down, that's when it emits light. We call this a photon of light. And if it drops this drop, it's going to be a UV photon of light. Here. And so, looking at the spectrum for hydrogen, we can map it out like this. This is called an energy level diagram, or we can just look at it like this. And so, if I have an electron here in the fourth floor, or actually, I missed one. An electron here on the third floor. If I have an electron here on the third floor, and it drops down to the second floor, then it's going to emit red light. This is the red light that we see in the hydrogen spectrum. If, on the other hand, the electron's on the fourth floor, and it drops down to the second floor, then this emits the green light. It's going to be a little bit more energetic. It's going to be green. If I have an electron on the fifth floor, and that electron drops all the way down to the second floor, then this emits blue light. If I have an electron on the sixth floor, and that drops down to the second, then this emits the violet light. And so these are the four colors that we see in the hydrogen spectrum, the red, green, blue, and violet lines. What happens if I have an electron on the seventh floor? If I have an electron on the seventh floor and that drops all the way down to the second floor, do you know what color light is? What's past violet? Ultraviolet. And so what we see is if we go from the seventh floor to the second floor, we're going to emit ultraviolet. And those are invisible, so we don't necessarily see that. So this is going to be UV. But it gets harder and harder to excite the electrons to higher and higher energies. So we don't get as much UV. And then we'll get infrared. If we go from some of these smaller jumps, like the fourth floor to the third floor, we'll get infrared, IR light. Okay, we're out of time, sir.